The gravity model is a powerful tool used in transportation planning to understand and predict travel patterns. It is based on the simple yet profound idea that the interaction between two locations, in terms of trips made, is influenced by their size and proximity. Just as gravity in physics describes the attraction between objects with mass, the gravity model in transportation planning helps us understand the pull that locations exert on travelers. Larger and closer locations tend to attract more trips, while smaller and more distant locations attract fewer. This model has become an indispensable tool for transportation planners, offering insights into a wide range of travel behaviors. From predicting traffic flows on highways to estimating the demand for public transportation, the gravity model provides a framework for making informed decisions about infrastructure investments and policy interventions. The gravity model's elegance lies in its simplicity and versatility. By considering just a few key variables, it can shed light on complex patterns of human mobility. This essay will delve into the principles and applications of the gravity model, exploring its strengths and limitations in understanding and predicting travel behavior. The gravity model draws a direct analogy from Newton's law of universal gravitation. Newton's law states that every object in the universe attracts every other object with a force that is proportional to the product of their masses and inversely proportional to the square of the distance between their centers. The gravity model in transportation planning borrows this principle, substituting trips for force, population, or economic activity for mass, and travel time or cost for distance. This translation allows us to understand how the size and proximity of locations influence the number of trips made between them. Just as a larger planet exerts a stronger gravitational pull, a larger city with more people and economic activity will attract a greater number of trips. And just as the gravitational force weakens with increasing distance, the number of trips between two locations decreases as the travel time or cost increases. While the gravity model borrows from physics, it is essential to remember that it is a model, not a law. It provides a simplified representation of reality and does not capture all the complexities that influence travel behavior. Nevertheless, its ability to provide valuable insights into travel patterns has made it an essential tool in transportation planning. The basic formula of the gravity model is deceptively simple, yet it encapsulates the core principles of the model. T_ij equals k times the product of p_1 and p_j divided by d_ij raised to the power of beta. Let's break down each component of this formula. T_ij represents the number of trips made between origin y and destination j. This is the quantity we are trying to estimate. P_i and p_j represent the masses of the origin and destination, respectively. It can be measured in terms of population, employment, retail space, or other relevant variables, depending on the type of trip being analyzed. D_ij represents the distance between origin y and destination j. However, instead of physical distance, it is often more useful to use travel time, cost, or a combination of factors that represent the impedance to travel. Kc is a proportionality constant that scales the model to match the overall volume of trips in the study area. It is determined through a process called calibration. Beta is a parameter that reflects the rate at which the number of trips decreases with increasing distance or impedance. It is also determined through calibration. By plugging in values for each of these variables, the gravity model can estimate the number of trips between any two zones. The accuracy of these estimations depends on the quality of the input data and the appropriateness of the chosen impedance function and calibrations parameters. The mass effect is a fundamental principle of the gravity model, reflecting the intuitive notion that larger zones tend to attract more trips. This effect is captured in the formula through the terms p_y and p_j, representing the masses of the origin and destination zones. The logic behind the mass effect is straightforward. Larger zones typically have more people, jobs, and activities that attract travelers. A bustling city center with a high concentration of offices, shops, and entertainment venues will naturally draw more visitors than a quiet suburban neighborhood. The mass effect highlights the importance of considering the size and scale of zones when analyzing travel patterns. It suggests that efforts to manage congestion and improve accessibility should focus on areas with high concentrations of population and economic activity. Section 5. Distance decay. The further the destination, the fewer the trips. Distance decay, another cornerstone of the gravity model, postulates that the number of trips between two locations decreases as the distance or impedance between them increases. This principle is intuitive. People are generally less willing to travel long distances, especially if the journey is time-consuming, costly, or inconvenient. In the gravity model formula, distance decay is represented by the term d_i_j, which signifies the distance or impedance between the origin and destination. The parameter beta further refines this relationship, reflecting the rate at which the number of trips declines with increasing distance. A higher beta value indicates a steeper decline, implying that distance is a stronger deterrent to travel. The choice of impedance function and the calibration of the beta parameter are crucial for accurately capturing the distance decay effect. Different types of trips and transportation modes exhibit varying sensitivities to distance. For example, commuting trips typically show a steeper decline with distance compared to leisure trips. Section 6. The concept of symmetry two-way streets in the gravity model. The gravity model, in its basic form, assumes symmetry in travel patterns. This means that the number of trips from origin I to destination J is equal to the number of trips from destination J to origin I. In essence, the model treats travel as a two-way street, with the same factors influencing trips in both directions. While this assumption simplifies the model, it may not always hold true in real-world scenarios. Factors like commuting patterns, tourism flows, and the location of specialized services can introduce asymmetries in travel behavior. For example, a suburban residential area may experience a significant outflow of commuters to a central business district in the morning and a corresponding inflow in the evening. Despite its limitations, the symmetry assumption provides a useful starting point for analysis. In cases where significant asymmetries are expected, the gravity model can be modified to incorporate direction-specific parameters or constraints, allowing for a more nuanced representation of travel patterns. Section 7. Calibration, fine-tuning the model for accuracy. Calibration is a crucial step in applying the gravity model. It involves adjusting the model's parameters, namely the proportionality constant k and the distance decay parameter beta, to ensure that the estimated trip patterns align with observed data. The calibration process typically involves using a portion of the available data, known as the calibration dataset, to determine the optimal values for k and beta. These values are then used to predict trip patterns for the remaining data, allowing for an assessment of the model's accuracy. The choice of calibration method and the quality of the input data significantly influence the model's accuracy. Various statistical techniques can be employed for calibration, each with its strengths and limitations. The selection of an appropriate method depends on the specific characteristics of the data and the objectives of the analysis. Section 8. Applications of the gravity model, from urban planning to retail analysis. The gravity model finds wide-ranging applications in various fields, including urban transportation planning. It helps estimate traffic flows on road networks, forecast transit ridership, and evaluate the impact of transportation infrastructure projects. Regional planning. It aids in understanding intercity travel patterns, analyzing migration trends, and assessing the accessibility of different regions. Retail site selection. Businesses use it to predict customer draw areas for new store locations, optimize distribution networks, and understand market potential. Tourism planning. It helps estimate tourist flows between destinations, assess the carrying capacity of tourist sites, and plan for tourism infrastructure development. The model's versatility stems from its ability to adapt to different contexts and data availability. By selecting appropriate variables and calibration parameters, the gravity model can be tailored to address a wide range of planning and analysis needs. Section 9. Conclusion: the enduring relevance of the gravity model. The gravity model, despite its simplicity, remains a powerful tool for understanding and predicting travel patterns. Its ability to capture the fundamental relationships between population, economic activity, and distance has made it an indispensable tool for transportation planners, regional scientists, and business analysts. While the model has limitations, particularly in capturing the complexities of human behavior and the influence of factors beyond mass and distance, its enduring relevance lies in its ability to provide valuable insights into the spatial dynamics of human interaction. As our cities grow, transportation systems evolve, and data availability increases, the gravity model will continue to play a vital role in shaping our understanding of movement and informing decisions that create more efficient, sustainable, and equitable transportation systems.